All right. Hello. Okay, we are on to our next lesson in our unit on diff-EQs, differential equations. So we've learned what a diff-EQ was and all the different forms that a diff-EQ could take. And we learned how sometimes we can't integrate or solve these differential equations, okay, given a particular solution. So we have methods to estimate graphs and points on the original function from the differential equation. So the first method that we learned was slope fields, right? So in fact, here's a picture of a slope field given right now. We're going to learn method number 2, which is using slope fields, but it's more of an algebraic approach to it. And we're going to use this method to help us solve for, or I guess estimate specific points given an initial starting point, okay, given that initial condition. So we're going to look at the same example as the one we did with slope fields first off, which is dy over dx equals x minus y. And there's going to be a few things given. So first off, one given thing is that that my initial condition, how about it, 0 is 1. So this initial point is given right here. And if I were to sketch this on my slope field here, it looks like I'm going down, and I'm leveling out, then I'm going up, up. It looks like I'm kind of following along this sketch here. So that kind of looks like my function, something like that. Kind of a little parabola-looking shape. Okay. All right, now, the idea of Euler's method, and I'm going to show you this on the slope field, but the idea is that we're going to start off with a specific point. And at this specific point, we're going to know the slope because we're given the differential equation. And it looks to be something like this, okay? And we're going to use this slope to trace out and approximate the next point. We're going to go along this line and approximate the next point over. And then from this point, we're going to figure out the slope there and approximate to the next point. And we're going to keep finding the slope at the current point we're at. And eventually, I mean, we're pretty much tracing along the curve using slopes. Okay? Using these individual little small slopes, connecting, making this jagged little shape all the way around our curve. So if I start at, say, 0, I'll be able to count along the slopes to estimate any point further. And it all depends on what your step size is. That's what they call it. Like how many x values you're changing at once. It could be 1, it could be 1/2, it could be 10. But the smaller your step size, the more accurate your point approximation will be because you have less room for error. So in this particular example, let's pretend like our step size, which we'll call the change in x, we'll call that our step size. We'll make it 1/2 in this case. So we'll say we go a distance of 1/2 every single time. So if I start off with an initial point at 0, 1, and we go a step size of 1/2, the next x value will be half, is at 1/2. Well, at 1/2, what can we approximate for the y value? Okay, what can we approximate for the y value? Well, this is essentially how we're going to set it up. Okay, I'm going to set up a little chart like I did with the slope field lesson. I'm going to put x comma y here, and I'm going to put dy over dx right here. Okay, well, I know that my initial point is 0, 1. And using my diff-EQ equation above, x minus y, which I'll put right here, x minus y, I know the slope at this point is going to be equal to 0 minus 1 or negative 1. Okay? And you can see that I traced that above right here on my graph, that it has a slope of 1, negative 1. So tracing along this slope, what's this next point going to be? Okay. Well, I know the x value is going to be 1/2. What's the y value going to be? Well, there's a simple way to figure it out. If I'm tracing along a line, so I'll redraw it right here. Like I'm tracing along this line of negative 1. If I know this point is at 0, 1, and I know this point is at 1/2 something, I can easily figure out that y value by just doing a little rise over run action, right? I'll call this y n plus 1 for notation purposes. That means the next y value, given that this is, I'll call this x sub n and y sub n, my current y values. And I'll call this x n plus 1, my next x value. If I want to know y sub n plus 1, it's just a slope formula. We're going to rise over run to figure that out because I know the slope is equal to negative 1. All right, so think about how that would look. It'd be y, and I'll call it n plus 1, minus yn, which I know is 1, over x n plus 1, or 1/2, minus xn, which is 0. And I know this equals negative 1/2. I'm tracing along this line to figure out this next point. And that's a simple thing to solve. We have 1/2 on bottom, so I can multiply both sides by 1/2. I get yn plus 1 minus 1 equals negative 1/2, and I can add 1 to both sides. Okay? So that ends up equaling positive 1/2. So my current point now that I just estimated was y was 1/2, 1/2. Okay, well, if I'm at this current point right here, I'll call that now xn and yn. If I'm at my current point, what would be the slope at that point on my slope field? What's the slope at 1/2, 1/2? Well, it's x minus y, or 1/2 minus 1/2. It's 0. Okay? So if I have a slope of 0, in fact, I'm not even going to draw out this whole equation again, because if I have a slope of 0, that means my line is going horizontal to the next point. So let's say I want to use that slope of 0 to approximate my slope at 1, the next step up. Well, if I have a horizontal slope going to the next point, it's going to share the same y value. So this next y value is simply 1/2. Okay? So, okay, I'll do one more. Let's say I want to approximate the next step up, or 1.5. We'll call it 3/2. Let's say I want to approximate this number. Well, I'm going to do so by using the slope at my current point, 1/1/2, right here up on the graph. So it looks to be a positive slope, but let's see what it is. At 1/1/2, that's going to be 1 minus 1/2, which is 1/2. Yeah, it's a positive slope. You can kind of see it going up right here. Well, I'm going to trace along that slope to figure out my next point. Okay. So what I have here is I'm going to use these 2 points with a slope of 1/2 to figure out that next point. I know that my yn plus 1, my next point, minus my previous y value, 1/2, so that's y minus y over x minus x equals 1/2. And I don't think that's too terrible. This is equal to, the bottom part here is equal to 1/2. 3/2 minus 1 is 1/2. And I can multiply both sides by 1/2. So I get yn plus 1, and I'm going to go ahead and add 1/2 to both sides. So that's 1/4 plus 1/2 is equal to 3/4. So my next y value is actually 3/4. So I started at the given point 0, 1, and I did a step size of 1/2, and I traveled along my slope field until I reached 3/2 to be 3/4. I approximated that point to be 3/4. But if you look up here on my graph, if I go over 3/2 at this point, yeah, that looks to be about 3/4. Okay, so I traced along the slope field to approximate that point. Maybe take a second, pause it, maybe look at that if you can. But I'm gonna generalize this equation in the next example. Okay? So I'm not gonna graph it. I'm not gonna show the graph because that kind of confuses people when I draw it. But the idea is that we're using the equation of your tangent lines. And I'm going to say lines plural. We're like using little mini tangent lines from one point to the next on the slope field. Okay. So think of the notation I was using before. We'll say that, you know, actually I'll do it this way. Think about how we figured it out in the last example. We said if we wanted to know the point yn plus 1, we did the slope formula. We did minus y sub n over x sub n plus 1 minus x sub n. And we knew those 3 points. And it equaled the slope. And the slope that it equaled was the slope at the point xn comma y sub n. Okay? This notation right here literally just means the slope at the current point. Okay? Well, remember how we solved it out. We multiplied both sides by the denominator, so we had yn plus 1 minus yn equals. We had that slope at the current point multiplied by the denominator, which was xn plus 1 minus xn. And if you notice, this is nothing more than the definition of an equation of a tangent line. This is a tangent line equation. Okay? This is the tangent line equation. We got y minus y equals slope x minus x. That's all it is. We're using tangent lines of many little slope fields to estimate points. But since we're looking for the next y value always, let's get that by itself. So I'm going to add this to both sides, and I have the following. This is Euler's approximation. He uses a tangent line approximation, but with fancy little numbers and letters here, to explain how we jump from one point to the next. Kind of a way that I always like to write it to help students out maybe is if I want to know, I have a current y value, so this is my now. If I want to know my next, I'm going to take the slope of my now and multiply it by, remember this was just my change in x, my delta x, or my step. So the last example was 1/2 plus my now. Okay, so I'm going to do the slope of my now times the step plus my current y value. And this is going to tell me the change in my y value to get to my next point. Okay, so this is the formula we use. And it's very procedural. It's not a terrible formula to use. And you can even see this formula pretty much just summarizes everything that I just said. Okay, so here is the finalized definition. Euler's method. So using small steps, we are going to use the slope at each point to jump to the next step and create an approximation for the solution curve. You can see how they write it right here is similar to how I wrote it before. To get, I call the new n plus 1, but if you do your new, you take your old function and add the slope at your current spot and multiply by your step. Okay, so this is, I call this yn plus 1. I call this yn plus your slope times your step. That's how you find your new y value. To get your new x value, remember, you just take your old value, and this should actually be add your step. Okay? And it even says it right here, where delta x is the step size, and this is the slope of the tangent at each point, at the current point you're at. Okay? So, I think once you see us do a couple examples, it's going to make a lot of sense. So I think that's what we need to do. We do at least 2 examples. Okay, it says use Euler's method with step size 0.4 to approximate values for the solution of the initial value problem. So here we're given our diff EQ. And I'm telling you, with this diff EQ, we have an initial point at 0, 3. And I want us to approximate 4 steps from that. The y value, 4 steps from that. Okay? Now, you don't have to draw out the slope field. You can if you want. I'm not going to. I'm just going to show you kind of the work that I like us, kind of how I like you to organize it. And I think this is a pretty, I do it in a table to organize it, like I did in the first example. All right, let's write out the formula so we make sure we understand it. I write it this way. If I want to know my next y value, I'm going to take my old y value, okay, and I'm going to add my slope at my current point, slope at my current, times my step. Okay? That's all it is. You're going to take your old y value and add the change in your y value and to get your next value. So this is nothing more than Euler's method. And I like to put it in a little chart as I go. So this is what I'm going to do. Okay? Try to organize the best I can. So this will be my points, and this will be my work, or where I do my dy and dx. Okay. So first of all, it says earlier in the problem that my step size is 0.5. So I can already do all my x values if I want. I'm starting off at the point 0, 3. And then I'm going to be going up by 0.4 each time. I'm going to do it 4 times. So I'm going to go to 0.4, comma, whatever. And then I'm going to go to 0.8 is another step size of 0.4. And then I'm going to go to, well, it says go 4 steps. So that's 1 step. In fact, I'm actually going to just simplify this out a little bit. We're going to go up to the 4th point. Okay, we're going to go up to the 4th point. So we got the 1st, the 2nd, the 3rd, and my last point, I'm going to make it be 1.2. Right? That's going up by 0.4 to my 4th point, just to make our process a little bit easier. Okay? All right. So basically what it's asked me to do is solve for or estimate the x value 1.2, given that initially we are at 0, 3. Okay? All right, pretty straightforward. Let's start by finding our derivative. My derivative at 0, 3, for instance. We got the equation, I'll rewrite it right here, y minus x squared. So my slope at this point would be 3 minus 0 squared, or just simply 3. Okay? So how the formula is going to work, and I'll just write it out here to the side. If I want to know my next y value, it's simply going to be my previous y value, which is 3, it's right here, 3, plus my slope at my current point. Okay, my slope at my current point is 3 times my step size. And in this case, my step size is 0.4. So I'm just using a tangent line to estimate my next point. In this case, I got that it was equal to 4.2. Okay. So my next point is 4.2. Okay. Now, sometimes, since the diff EQs can be kind of complicated and annoying, because now, if I want to know the slope, this is the same thing as doing 4.2 minus 0.4 squared, which can be a long decimal. I like to just go ahead and write the full thing out. Let me explain what I mean. It's going to be y n plus 1, so my next y value is equal to my previous y value, which is 4.2 plus. And then remember, the next value is my slope at my current point. My slope at my current point is 4.2 minus 0.4 squared, right? Instead of just writing that out, I just went ahead and put it all into one formula. Okay? Instead of just writing it out like I wrote 3 up here, I went ahead and wrote out the work, so I don't have to end up rounding decimals that might be long. So I'm doing my previous y value plus my slope at my current point times my step, which will always be 0.4. Okay. And until you get to your final answer, keep all the decimal places. I got 5.816 here. So this is 5.816. Now, to get my next and final y value, it's going to be my previous y value, so 5.816 plus my slope at my current point, and we're using the current point that we have. So that's y minus, or 5.816 minus 0.8 squared. So that's y minus x squared times my step size, 0.4. And I encourage you to pause the video and see if you can get this on your own, but I got that ended up being 7.8864, and so that's my final answer. So I went up 4 steps, or 4 points, I should say, to estimate this point to be 7.8864. So I'm using Euler's method, and I approximate 1.2 to be 7.8864. And as long as you kind of, please try to keep it in a chart, nice and organized, because if this is a free response, this is a very well organized plot of work here to help you solve your equation. Okay. All right, let's do one more. Yeah, we'll do one more. Okay, we'll call it after this. So it says use Euler's method to approximate blah. So I got this differential equation, which we've seen a lot of, and we have a step size of 0.05. Okay? And our initial condition is 1/2. Okay? I know at 1/2 that the y value is 0. So I'm going to start there with a step size of 0.05. And I am going to go from my starting point, 0.5, all the way to 0.75. I want to approximate 0.75. Okay? All right. Well, let's set it up. Okay? So what I'm going to do is, if you want to write the formula down, it doesn't hurt to do that. This is Euler's formula plus dy over dx at my current point times my step. Okay. Make your little chart. Give yourself plenty of space. Okay. And the point we're starting off at is at 1/2, 0. And we know that we're going all the way to 3/4, and we're stepping up by 0.05. So if I got 0.5 as my step, 0.05 plus 0.5 is 0.55. And then another step up would be 0.60. Another step up would be 0.65. Another point up would be 0.7. And then finally, my last step would be 0.75. Okay. Now, I know we're only going from 1/2 to 3/4, which is not a huge jump, but if I'm stepping by 0.05, that is a lot of steps in between. But the good thing is, because it's such a small step, my answer is going to be that much more accurate when I get down to the final. Okay, because we're not leaving much room for error. All right, use your formula here. And I recommend you can kind of skip through the work if you're wanting to, but I'm going to write out all the work and the final answer. Okay. All right, the setup. If I want to know my next point, this is equal to my old point, okay, which is 0, my old y value, plus my slope at my current point, which is x minus y, or 1/2 minus 0, times my step size, or 0.05. And whenever I do that, I get 0.025. So I'm going to put 0.025 as my next approximated y value. Okay, so now if I want to approximate 0.60, I'm going to take so if I want to approximate that next y value, I'm going to take my current y value, which is 0.025, and I'm going to find the slope at my current point, which is x minus y, or 0.55 minus 0.025. and multiply it by my step. And this is the work every time. If you can just remember this formula and set it up this way, you're going to be completely fine. I got 0.05125. So I'm going to put 0.05125. All right, I'm just going to keep going. Next point. All right, my old point, okay, which is 0.05125 plus, and then the slope is going to be x minus y, or 0.60 minus 0.05125 times my step size. And I got 0.0786875. Notice I'm keeping the full decimal here. This is why I'm leaving plenty of room. And I know this seems tedious. That's what it is. It's tedious. But I have seen them ask this far before with steps. Okay? So then my next y value is going to be my old y value, so 0.0786875 plus the slope at my current point, so x minus y, or 0.0786875 minus 0.65. Oops. That should be the other way around. I apologize. I misspoke. It's x minus y. Sorry. So x minus y. So 0.65 minus 0.07. Sorry. Times my step size of 0.05. And I'm getting 0.107253125. So I'm going to put that right here. 0.107253125. And thankfully, I only have to do it one more time, and I'll be all set because I'm looking for 0.75. So my next point is equal to my current y value, or 0.107253125, plus my plus my current slope, which is 0.7 minus 0.107253125 times my step size of 0.05. And whenever I grade your work on this and I see people go down the line, it looks like a little like pyramid because your work is getting longer and longer, so it makes this little triangle pyramid looking shape of work. But whenever I do that, I'll just go ahead and write the final answer. Final answer I got was 0.136890468. And if it's your final answer, you can round. If it says 3 decimal places, round, but I wouldn't round until the very end. Okay? So there's your approximation of the 0.75's y value, given that we have a step of 0.05 starting at 1/2 0. Okay? That's as long as you'll probably ever see it, but it's tedious work. And I probably could have got it wrong here because I was going kind of quick. But I wrote out every single decimal, and I typed out every single decimal in the calculator each time. And if you can show me this work, you are set for method number 2 of dealing with differential equations. Okay? All right, well, we finished a lot today. Tomorrow, I hope to review the video and then actually go over the final method, separable equations. Okay? We know how to do it geometrically and numerically. Geometrically, we use slope fields. Numerically, we do Euler's method. And analytically, we're able to solve doing several equations. So my goal is to get to that point tomorrow. All right. Well, right shy of 30 minutes. So good job. Appreciate y'all paying attention, and we will review all this tomorrow. All right.